Right, so this is lecture 4. We are going to learn about groundwater contamination today. Mostly, you should be able to calculate how fast the pollutants can move from in groundwater after a spill, or if you have a contaminated site, how this is going to move from that site. Part of the projects, you will pick a site. If some of you pick a site, then you have to calculate how far these contaminants will migrate, let's say 10 years from now, 5 years from now. So this class will be helpful for you to make that calculation. And if you took CE153, you already know the background, but I'm going to go through again for the same thing. But this in this class, we'll just use more examples. All right, so one thing I just want to keep repeating that if you have not joined on Campusware, that's where I really want you guys to join, because we'll start discussing about projects and everything else in that particular site. This will be helpful because anytime you want to come back and see what has been discussed, it's all there as opposed to email. And today we will form the group if you have not done it. So this is not next Thursday, this is today. Um, so I provided those projects so that you have some ideas. And I just want to tell you that that topic is not final, in the sense you may decide a topic today, but before we start working on outlines, if you decide that this is not a topic that you as a collectively, if you feel like this is not something interesting enough, or you don't have enough data or enough information, you can modify the topic. But just make sure that homework is due today. If you have not uploaded, do it by midnight. Quiz 1 is going to be released today after the class at 7 p.m. So class over at 6, so I release usually 1 hour after that. And you can take any time within next 24 hours. And we'll decide project team today. And the reason we want to decide project team is because your project topic is due next week. And when I say project topic, it's you got to think of at least a title, and that title is not final. You can change it, but you got to write at least a paragraph about the scope. Scope means, what is this project about? For instance, you cannot say that I'm going to work on landfill. That's a very vague and very not specific. So when you write the title, it has to be at least get some idea about it, and then you write a paragraph talking about the specific nature of the project. For instance, you could say that if you said your project is going to become on landfill, you could say we are going to explain or we are going to explore the how you design landfill to minimize some kind of leachate that comes out of the landfill. So that's specific. Or somebody else could say that we are going to understand the design that could improve the energy production in landfill. So these are the different types of specific nature you have. And homework 2 will be released today, which will be due next week on Thursday. That's based on the groundwater pollutions and whatever we learned so far. Quiz again, quiz 1 today, that will release at 7 p.m. 10 multiple choice questions, each question's 2 minutes, so you have 20 minutes. Unless you go through CAE where you get extra time for your accommodations. Um, Again, clock start and the moment you open it. When you open it, it says, it give you instruction and it will ask you if you want to proceed. The moment you click proceed, that means you have 20 minutes from that time. And submission window will close at 7 p.m. tomorrow. So that means by last, I would open it 6:40, because if you open 6:50, you still have 10 minutes maximum, because 7 o'clock it will close it. Again, the materials that is covered for the quiz is 1, 2, 3. So you can, if you look at your lectures, you should be able to answer most of the quiz. And this is again open book. So you have all the materials on the slides or anywhere you want to find out. But don't discuss with your friends. All right, so project team, we are going to do it today. I want to suggest that again, I recognize this is difficult for you to find a team if you're not seeing each other. So that's why we're going to do it now. And just to reiterate, maximum 8 members can be allowed in a team. And if you don't have a team, let's say you communicate with each other. Then if you don't have a team, let me know by campusware so that I can put you in some teams. And if you already have a team and if you have some space open, you could always say that. But what we're going to do now is just write team A, B, C, D, and just see whoever here. No, we can just makes it easier. Um, so project topic, I just want to say that you this next week you'll discuss with your team members and decide a project topic, and hopefully that you will not change it. But sometimes students change after working. When they start working on the outline, they realize this is too much or this is something they can't do it. So then they decide something else, which is allowed as long as your outline is not done. But this is will just get the conversations starting. Okay, so let's form a team now. Just example, I put team A. I just write team A. It's not like you got to come up with a name if you want to call your team something else based on your interest. I mean, you can call whatever word that makes it connecting for your team. So I just write team A, B, C just so that we can write it right now. So I know Joe Lee, he sent me email about the teams that they are forming. So they have 7 members. So let's put in other teams before we add another person here. So I know that other all some other you send me email. I didn't write it here. So let's start with those who already send me email. So if you can um, either team B, that group, if you can start writing your name or you I mean, your whoever the next team, I'll start writing their name here. So you can write in the chat window that this I'm. Let me see what the chat window. So I know some of you already made teams. So how about you start? Let me see. Any other who form a team already, and at least 2 or 3 students in that team. You can tell me, and I write your name. All right. So I guess most of you um, are silent. So that means, Emma, you already build a team, right? So at least I know your team member. So I'm going to write team B, Emma.
Oh,
You
I
know,
put our team in the chat.
okay. Let me write. Look at those. Okay, I see you're already writing them. That makes it a lot easier. I don't have to even type them. Okay, so I'm going to write the name at the last name here, or first name. So Emma, Catherine, then Kija, Anika, and Hannah, and then you have Emily, then Kiko. Right, so 1, 2, 3, 4, 5, 6, 7. Okay, we have 7 members. Team C, we have 6 members. Jane, um, I'm just typing whatever comes here now, so it's not like team ABC. We'll change the name. Jenny, then Nuda, Eden, Matthew, then Cell. Okay, so we have 1, 2, 3, 4, 5, 6. So anybody who is not in the team, you can join any of them. So let's see. Team D. We have David, um, And again, you can change theme until you start writing the outline for some reason if you want to change. But obviously, that depends on the team you are going to join. That has to be not filled for you to change the team. Natasha, very rarely people change, but just I don't want to. So we have 5 members here. So that means we have at least 3 members here missing. Um,
Professor,
yes.
it'd be helpful to have this as a like Google Excel that everybody could edit and just like type in their group's names.
Okay. So what I'll do is let me do one thing. I'll share a Google Drive, a Google Sheet with all your name, which is already there, and then you can change if you want to. If anybody else want to add their name, they can just we can update that. That way we don't. But at least I know that 1, 2, 3, 4, 5, 6, 7, um, almost 8 members are there. So at least I just want to make sure there's an initiation between teams. All right, so I'm going to copy all these and save it in my, just in case I lose this chart window for any reason. Usually it's save it, but I want to make sure that. Okay, let me check that. So anybody who has not formed a team, you can update, put yourself. And what we can do is um, you can also write your title of the, or you don't have to write title because you have not decided yet. So if you have decided, that's fine. All right, so I'm not going to write it here now just to save time. Um, let me know if you don't have a team yet. Okay, I'm going to put you in one of those teams based on your interest and topic. And I'll write all the names before I release the annotated slide, so that way everybody knows which teams who are. Okay, so that's all. Um, what I wanted to suggest that you are going to write the project, so you should also know how each lectures or class is going to help you. Again, I just want to make sure that not all the things that you learn in this class will go to your project. You don't have to include everything. For instance, if your project has nothing to do with the groundwater, you don't have to do some calculation on groundwater. So that's why I'm just putting it here so that you know whichever lectures topics are helpful for that project. So on lecture 1, we learn major environmental laws that drive waste management, and projects like where you have policy and other things, that's going to be useful there. Lecture 2 is we learn about how to identify the contaminants of concern for a hazardous site and their properties. So that means at least you know what kind of contaminants to look for. Because there is a list of pollutants in that chapters, you should be looking for those. And lecture 3, we learn how to predict the concentration in water, soil, or air based on their thermodynamic properties, at least to see which one will move more than other. Um, for instance, adsorption, you will be able to predict which one will adsorb to the soil more than any other contaminants. And this will be useful if you have a site which has different pollutants and you want to know which one will move through soil much faster. So that's why that particular lecture will be helpful. Lecture 4, which is today, what we are going to learn is to predict the pollutant transport in groundwater from a spilled site. So as you see over here, we are going to look for more thing about contaminant plume. Again, just a picture that shows that. For instance, this is a gas station. Gas station has an underground underground tanks, and that's the pollutants released here. It will all slowly migrate through subsurface or unsaturated soil, and then once it hit the groundwater, then groundwater flow will make the contaminants move. So part of your projects, you are going to calculate that. If you have a site, you know the site locations, you know the soil properties, you'll be able to calculate how far from that site contaminants will move. So these are all the different questions that you should be able to answer. I don't have to read it here. Basically, you have to answer how far, how long, when. So those are all the conditions. So what you learned today in this class is to make that calculations for your project. So what we learn in next couple of slides is fundamentals of plume transport in groundwater aquifer. So let's think of now what different processes that make pollutant move through soil. So imagine, anytime I do this kind of work, I always think myself as a pollutant, and I picture, I visualize what it feels to be inside the groundwater. So think of groundwater. Pollutants are nanometers or lower than nanometer size, and the pores inside the groundwater is a micron size. So that means 1,000 times bigger than that. So now you think of, imagine inside the room, that's how the pollutants feel, the pores, and they move through the pores, and the walls are the soil surface. And why pollutant will move from A to B unless there is a force behind it. So in groundwater, the main force is the advection, so the flow of groundwater itself. If the groundwater doesn't move, pollutant doesn't move that much. But that means if you ask question, if what if the groundwater flow stop? Does it mean that pollutant will not move A to B? Well, it moves, but not that far distance. What it does, it will disperse, and that dispersion, why it occurs, all that you will learn a little bit here. So that's how we know that there are three processes that makes pollutant move from one location to another. One is the flow of water, that's advections. Another is dispersion. Dispersion means if a pollutant move, it hit a wall or somewhere, then it divert from, because flow is diverted because of obstacles, and that's why it disperses. So why it is important? That makes the pollutant diluted and spread around from the locations. And the pollutant disperse around the entire, the plume disperse, then you have to have multiple sites for treatment. So that's why it's important to know how much it disperses. And also dispersion is important because it dilutes the pollutants. That means the concentration will decrease just because it is diluted. And pollutant can also move by diffusion. Diffusion means it's a molecular process. That means, imagine you have a molecule. Um, that means, if it hits the wall, then it's a dispersion. But diffusion means the medium itself, the water molecule itself, vibrate because of temperatures. They move around Brownian motion or random motions. Because of that, the pollutant itself also stick, not stick, they hit with water molecules and they will move around. And that's because of the reason you can see that in the air itself, you can see the dust move around in a random motions. And that movement is much more higher inside the room if the temperature is high, because the thermal energy in the air is much higher. So diffusion again depends on the how big the molecules are. So diffusion, I'm just going to write it here. Uh, Diffusion increases if the mass or the size of the pollutants is decreases. The reason is that means if the size is small, it can be hit by water molecules, or the force is sufficient enough to move them. So that means if you have a big molecule, the diffusion will be a lot less. And another reason, that energy of water is depends on the temperature. So that means if your thermal energy is more, then your diffusion would be much higher. So that those are the two factors you have to think for: mass or molecular weight. Okay, so this is I'm writing molecular. So these are kind of quiz questions for the next time. If I give you a molecules and I just show you the structure, you just look for which one is heavier. Look for molecular weight. You should be able to say which one will diffuse more or less. Dispersion, again, that depends on how much times it's going to hit the wall. So that means how much the porous is. So if the soil is very porous, that means it's more likely to flow faster. So dispersion will increase if the media is packed heavily. So that means it depends on the bulk density. Bulk density means how close they are packed. Okay, if they are packed completely, let's say pure solid, bulk density is 0. That means our bulk density is not zero, density can be zero. That means there is nothing, it's vacuum. Ball density is very high. There is no pores inside it. So if your pores are very small, that means you're it's more likely to disperse. So that means if your aquifer is sandy soil, and the pores are bigger, then the mechanical dispersion will be less. If your pore is clay soil, that means it's more likely to disperse because of that barrier. So again, so that depends on porosity. Okay, so the porosity, the dispersion increases if ball density increases, and ball density means how big how if you know density, what is density means? Density means mass of a particles divided by volume of particles. But if you do the same thing, mass of soil, aquifer soil by volume, it's not just soil, it has void inside it. So that's why the density is actually ball density is lower than the actual particle density because of that space. So if the ball density is higher, that means it's very compact. It's going to disperse it more because it's bounce around. And ball density is more if the porosity is less. So, and advections, how stop move is all about how fast water moves. And so that means if the velocity of water is more, advection will be more. So this is velocity of water. Right, so these are the conceptual process that you should think of before you try to understand how things works. And then these are the three processes by which contaminants can spread or move from A to B. But there are processes that could also decrease the transport. And those process, two example I gave, one is adsorption. We learned that in last class because as you see there are more pollutants, they're going to stick around. And if they stick around the soil, the water will move around, but the contaminant will left behind. And so that means it slow down the transport. So again, we learned adsorption in the last class. You know that adsorption depends on, which is Kd, uh, that FOC, fraction of organic carbon, times KOC, or affinity of organic, that pollutants towards organic carbon. Again, this is only applied if it is sticking with only organic carbon. If it's not sticking with organic carbon, everything else like clay, this equation is not valid. So again, you have to think of which pollutants you have, and then you have to think of all that. And we also know that KOC, that means affinity of contaminants to our organic carbon, can vary with type of organic carbon. And we know that in nature, organic carbon can vary at different types. So that's why a lot of times experimentally they determine affinity of pollutants towards octanol. Octanol is a specific type of organic. So KOW, octanol water coefficient. So this is something you can find out if you Google it for any pollutants, and then you can able to compare between different pollutants which you have in your at your site. So that means if you see KOC is some constant, so I'm just going to write 8 times. So this is just arbitrary constant. Okay. So if you substitute KOC here, you'll be able to calculate KD, and FOC is the fraction of organic carbon in soil at your site. Something that you have to assume if you don't have a number, or you could you have to find that out. So all right, so you now if you know all these numbers, you will be able to calculate that adsorption fractions. The last one is degradations. Degradation can occur because of chemical degradation. For instance, if you leave behind a pollutants in exposed to sunlight, it can degrade because of sunlight. Or that's the chemical degradations or photo degradations. Sometimes you have also oxidants or reductants in water, and when it react with that pollutants, it can also degrade. So you have to also think of those aspects. If you know redox process, then you will be able to do that one. Again, these are things you have to go through, thinking through when you have a site or a specific project, you will start thinking of on this line. And I'll help you out in that project. I'm just laying out all the framework here so that you know which one is relevant for you. And if you are if the pollutant can be biodegraded, that's the time you have to think of all that. And we'll learn biodegradation later, so I'm not discussing more too much, but just know that these are the different process. Adsorption KD, biodegradation, let's say K. Okay, so if you know you want to have those two K value to be able to calculate how much pollutants remain in the at the site. In this class, we are going to mostly learn about how contaminants move just by adsorption or just by flow. So for different sites, you have to also compare how far it can migrate. What controls is the hydraulic gradient. Hydraulic gradients means, think of this way: if you pick a glass of water and at a different height, and you connect them with a pipe, it always moves from the higher to lower. So that's the hydraulic gradient. Means the heads are different. The water height at two different locations are different with respect to surface of Earth. So that's the exact same concept. Here you are arbitrarily defining a location very bottom, so that we call datum. And we are just looking for how far the water table height is, and that was total head. So for instance, here, this is the height, this is the second height, H2 and H1. So that means you have to look for which height is bigger, and water moves always from high head to lower head. That's why water moves from mountain to ocean. So you know the height, and if you know the height, the difference in height divided by distance is called hydraulic gradients. And if you know the hydraulic gradients, that's the driver, and you'll be able to calculate which direction is going to move. It's very important at the site because you have to know the elevation, what's the elevation or topology in that particular topography for that site, and you have to also know the groundwater directions. And usually you'll be able to find that in USGS site if you are doing that, if your site is in US. And we'll help you out. Honest will help you out if you don't have that information. All right, so now that you learn what forced the water to move, now question is why it moves different speed at different aquifer. Again, what affects that speed is the pore space that you have inside the aquifer. If you have more space, think of you can move much faster if it's not too crowded. That means if your pore space is higher. But if I ask you to run through a small cave, you can't move faster. It's exactly the same concept here. Porosity is the concept of how much pore space you have in the groundwater aquifer. So if you have more space, that means you have more less frictions, and then you can move faster. So porosity is something that you have to calculate for your site. And so the way you calculate is you have to calculate the void space in a small amount of soil. Void space means the space inside divided by total volume of the soil, means including the volume of soil. So if I take a cross section, think of your particles are here. So that means all these are particles. And this is, let's say, this is particles. So if I ask you what is the pore space here, then you have to say what's the total volume. Total volume, if your side is A, then the total volume is A square. And if I ask you what is the the pore space, that's basically let's see if I let's say the watercolor is this. So this is your pore space. Okay, so that's your this is your B void. Okay, the color. So that means if I give a simple example, I say what is the, this is a sphere or circle of radius r, and then you have this radius is a. And if I ask you what is the porosity of that medium, so this is your soil, and this is your pore. So if I ask you what is the and imagine this is a 3-dimension volume. So what is the porosity? So that will be the porosity will be, let's say, n or n whatever the symbol people use. That would be the pore space, that means the void space, which is the sphere. So if you know what's the sphere volume, that's 4 by 3 pi r cube. That's the volume of a sphere if the radius is known. So that's the void space. And if you think of the what's the total space, that's about this one. So a cube. Okay. So this is just one example. So this is just a simplified way to calculate it. So that means if I give a structure and I tell you this is the orientation, you should be able to calculate. But just know the concept of porosity. And again, bulk density is, if I calculate the bulk density here, what that means is bulk density, I'm just going to write it. Bulk density is the total weight of the soil. So weight of soil inside that volume divided by volume of soil. It's a total volume. Voids volume. Okay, so that's the total volume, including the void space. So weight of soil, you know the density of soil, and then you multiply times the volume of soil inside, then you can get the weight of the soil. So this is just the concept how you can calculate all that if you have to. All right, so you learned the porosity, and the one last thing that affects water velocity is the viscosity. And you might ask question why viscosity of water will change. Well, viscosity of water can change if you have more salt. For instance, if you have a ocean water or sea water, it has salt. It makes it more density or denser, and then the viscosity will be higher. And the viscosity can also change because of temperatures. So if your temperature increases, it become more, the water molecules, they will expand because they will bounce around, so it will expand. The whole entire water volume will change. So higher temperature, lower viscosity. And if it's saltier water, it's more viscous. So that's how we can change. So viscosity of water will increase if temperature decreases. Or if it increases, if you have salt concentration increases. Okay. Again, these are just concept. And so if you, now that you learn all the concept or background, the key is to calculate the flow rate, how much water is going to flow through a system. If you are creating a barrier or you're designing a treatment system, you have to understand that flow rate in a system. So Darcy's law, which is basically, what it means, that it says the flow of water is proportional to the head difference, which is the driver behind the water flow, times the hydraulic conductivity. Hydraulic conductivity is basically like thermal conductivity. Some medium allow the temperature to flow faster. Same thing, some soil allow the water to flow faster. And we already know what could be the reason. We know porosity, all that factor, but as a whole, we call it hydraulic conductivity. So that's hydraulic conductivity is a function of both soil properties and water properties that we learned that just few minutes ago about this. So we'll connect that. But just know that if you want to calculate how much flow through your system or through the locations, you will use these equations. So the Q is the flow rate. K is hydraulic conductivity. That's length over time. If you are saying the dimension, flow rate is volume over time. So that means this is LQ, length divided by time. Area is a length square. Okay, so that's your dimension. And dH over del, which is the hydraulic gradients, how far the head drops as a unit distance. As you see, h is the height and or the length scale. Dl is also length scale, so that means this will be L over L, which will be dimensionless. Okay. So one thing to note here is that when you have a site for remediations or if you are looking for assessment, you have to think of what kind of materials they are made of, because that determines their hydraulic conductivity. So for instance, if you know it is a sandy soil, so you know the sandy soil is highly porous, things moves much faster, or it doesn't stick to the water that much. So you see the hydraulic conductivity of sand is much higher. Um, and if you look for gravel, gravel is much bigger. Anything larger than 2 millimeter, we call gravel. Okay, that's the based on size definitions. So if the size of it's like the too big size, then they have much more void space because they cannot come close that much. So because of that, inside the gravel, it moves much faster. So you have all the other factors are there. I can check. Limestone is much lower because it has very small fractures. And then what's important here is the clay. Clay has very low hydraulic conductivity, and it's not because it is the reason it has very low hydraulic conductivity is because the clay particles are very small, but it has much more void space. The way it works is, imagine this is a sand and another sand here. Okay, so if I say what's the void space, then you can say this is the void space, right? So that's where water will move. That's your water move this way. But imagine you have two clay aggregate. Clay aggregate means you have to think of there are many particles like this because clay size are 2 microns or around small size. So we have a lot of particles like this. I'm just putting a number here. So if it is sand, water cannot penetrate through sand. But if it is clay, now imagine the same volume, you have the same size as a clay aggregate, but it has inside it is a lot of small fine pore. So that means it's still porous, it's much more porous than in many cases, but they are so close to each other, the particles are so close to each other that water itself is tightly bound because of capillary. Here, in the large, when you have sand and gravel, they are so big that the capillary doesn't exist because capillary the pressure depends on the how close they are together. So that's why if you have a clay material, even though it has high porosity, it has lot lower hydraulic conductivity. If you take the clay out, once it becomes silt or sand, as the particle size increases, the hydraulic conductivity um, increases. So this is where I connect together how hydraulic conductivity depends on many factors. So let's see if the equation is correct or not. Um, I think a lot of times I made this mistake before, so I just want to check. Um, this is increasing hydraulic conductivity. That's basically how this I talk about that porosity. The hydraulic conductivity is increases if the viscosity decreases. Okay, so that's why I say there is a mistake here. That has to be mu here. Um, and I think this is I'm just going to write it here, the correct one, so that nobody confused. So this is K by mu. If you see the proportionality, so that means if the intrinsic hydraulic conductivity increases, the hydraulic conductivity increases. If the viscosity decreases, the hydraulic conductivity will increase. All right, so that's all in terms of the flow of water. I just want to revisit again just to say that this is Darcy's velocity. Darcy's velocity is just a concept. What it means that if you hypothetically, this is the flow of water, but it doesn't mean that what it does, it assumes that water flows through the entire area. So that means if I take a soil cross sections, Darcy's velocity assumes that the entire velocity move this way, and there is no pore space in between, which is not the case because you have soil. So you can have soil. I'm just going to make like this. So you have pore space. Let me make it correct. So this is, let's say, this is soil materials. So that means water is going to move through only through the pore space, and Darcy's law doesn't account for that one. So that means if you want to calculate actual velocity of water, which is Vs, seepage velocity, you have to divide Darcy's velocity divide by porosity. So that's just a concept we learned in the fee 153. I just want to reiterate again for you to calculate. All right, so we'll learn at least to some concept, the background before we do start doing the calculation. So I'm going to see how much we learned so far. So we have this generic quiz. You know which one has high porosity. So you should be able to, storage capacity means how much pore. So think of that. The more pores, the more storage. So now you tell me which one has more porosity. This is a tricky question. The moment I see this one, I didn't really cover it that much, but just I discussed to some extent. Silt size is, if I say this is the size increases this way, okay, that's all I'm going to say. This is around 2 micron. This is 2 less than 2 micron. This is 2 to 75 micron. 75 to 2 millimeter. Gravel is greater than 2 millimeters. That's the size, okay? So this is D. All right, so I'm going to close the poll in 3 seconds. So whichever answer you can give, I'm just going to close it. Okay, so end poll. This is a mixed result. The answer the question on the slide. So the reason what I didn't tell you is that if I have the ABC, then obviously you can answer this very easily. The clay itself has a lot high porosity, so that's why it has high. Usually, that's the high storage capacity. Doesn't mean that you can receive all that water because it's very hard to extract it. All right, so that's fine. This was a little bit tricky question, that one, but let's solve these particular questions. The height, estimate the groundwater.
Professor?
Yes.
Sorry, I just wanted to clarify. So the final solution to that was clay?
Yes, yes. But that you not be able to guess unless I gave you that porosity tables, okay? Because usually I accompany that with a porosity table. So whichever has highest porosity, it has more storage capacity. Okay, so that's all. I'll say storage capacity is increases if porosity increases. Okay, so you got.
But isn't,
yeah.
wait, I'm sorry. So what were the values that you wrote right next to this?
Those are the size of the particulates. So clay
Okay, thank you.
individual particle size. So this is particle size. Okay. Particle size. So anything we call gravel, this is a definition. Gravel definition means any particulates bigger than 2 millimeters. So as the particle size gets smaller and smaller, the pore in between particles size also decreases. So if I ask you the same question, which one has highest hydraulic conductivity? You will say obviously gravel, because the size is big, so that means the pore size also going to be bigger. Okay. Or pore space between particles are going to be bigger. All right, so now that we learn this Darcy's law and all that, let's try to solve these questions. It says estimate groundwater flow. The hydraulic gradients of groundwater in a certain location is 2 meters by 100 meters. The reason it says 2 meters by 100 meters, that means if you travel 100 meters, the head will drop 2 meters. So this is 2 meter drop in head. Okay. So if you're two location A to B, the difference between the distance is, and this is H, let's say this is H1, H2, groundwater move these directions. Okay, so then it will, um, I'm just putting in notations. Okay, a lot of times people write different way. Um, just give me a second. Let me make sure this doesn't make noise. Right. So so there is a question I didn't see in the chat window. If you can move faster in more porous media, why is dispersion higher with a higher bulk density? Um, so let's see the question. What does that mean? If you can move faster in porous media, why dispersion is higher in higher bulk density? Um, Actually, it's a good question. I didn't really, I skim over through it. If you think of mechanical dispersion, let's see where we discuss that. Mechanical dispersion means, let's see here. Dispersion means, how quickly a water can move around, right? So this is what dispersion means. So there are infinite number of ways that water can move, right? So that's how it can disperse or spread around. So you have to think why it spreads. It spreads because it has obstacles. So when it has obstacle, if it finds something close to each other, then it's always find another route. But that dispersion actually, um, not just what's the bulk density, it's also on velocity. If it is moving faster, it's more likely to disperse faster because it hits at location, it just go around. It's like a spring to another locations. So dispersion actually is a proportional to velocity of groundwater. So if high velocity, that also disperse. And also if it has more obstacle, that means if it has more porous media, it also hit. So there are, I think, just writing the bulk density, that's not accurate, because if you have low bulk density, what it does, it also slow down the water. If you slow down the water, dispersion also decreases. So I got to think of all that when we actually calculate. So it's not as simple to say bulk density. It has to move faster. So this is the proper way to think. If something move faster, then it's more likely to disperse because it hit some location and it move far away from that locations. Okay, so let's solve this one. So what it means, it keeps the hydraulic gradient. So dH over dL is 2 meters. That's a drop in height. That's dH, and this is the dL or L, 100 meters. So that's 100 meter. So you got 0.02. There is no unit here. Here, groundwater flows through sand with a hydraulic conductivity equal to 40 meters per day. And so K is 40 meters per day. And the porosity, so porosity is 0.5. That means 50% of the entire soil is void or filled with air, or it doesn't have, it has pore space, 50%. 50% is soil, another 50% has space. An oil spill has caused the pollution of groundwater in a small region beneath an industrial site. How long would it take for the polluted water from that location to move from that location to reach a drinking water well located 100 meters down gradient? It's basically asking how long it will take for pollutants to move from 200 meters distance. Assume no retardation of pollutant, means assume no adsorption. So all it is saying is how quickly pollutant moves. Here it says pollutant doesn't degrade, pollutant doesn't retard because of adsorption or all that. That means the only way the pollutants will move is because of how fast water move. So that means if you think of velocity of contaminants, it must be velocity of water. The reason is it doesn't have any adsorption because no retardations. And now you have to calculate velocity of water. Well, velocity of water is Darcy's velocity by porosity. And Darcy's velocity, you know, is k dh over dl. Okay, that's the Darcy's law. The area is cancelled because the velocity. The flow rate is k dh over dl times area. That means flow rate divided by area is velocity of Darcy's. Okay, so that's how it is. All right, so k is 40 meters per day times dh over dl is 0.02 divided by porosity is 0.5. So if you make that calculation, 40 times 0.02 is 6, 8, 0.8 divided by 0.5. So that will be how much? So 16, 1.6. Check that if it's right or wrong. I don't. Okay, so that's the velocity. So now you know this. This is how fast the contaminants move, the pollutants move. What it says that it means it moves 1.6 meter per day. So I ask you how long it will take for polluted water to move a location 100 meters away. That means how long it will take to travel 100 meters. So that means the time would be distance by velocity of contaminant. So distance is 100 meters and velocity is 1.6 meter per day. Will give you whatever that number. So 100 by, if I calculate, let me calculate that. 100 divided by 1.6, 62.5 day. Okay. Let's see. Okay, so that's all for the answer. So that should be the answer. Any question? All right, so let's see the quiz, another quiz just to see. Relaunch. Which type of aquifer materials would allow water to move faster? And usually in the quiz, in the midterms, I ask also why, and you'll have to also explain that. And the answer is already given on the table. You just have to see which one is fastest. Silt is not given here. Imagine silt is something between the size-wise. Silt is smaller than sand, larger than clay. Okay, so I'll close in 5 seconds and I'll explain it. All right, so share the results. So as you see, the as I said, silt is smaller than, so you have to think of which one move faster. Clay, you know that clay distance is this much. It move very, very slowly. Sand is 41. So obviously between sand and clay, you have to choose sand. And now silt is not given here, but I told you silt size is always is bigger than the clay size. That means it must allow water to move a little bit faster because capillary will decrease as the size increases. So the right answer is sand. So what we learned? We learned that um, water can move faster if you have high porosity. After the break, we'll take 10-minute break. We'll learn about once you include adsorption, because in most of the contaminants will not be non-reactive, it will stick with soil, and how that will affect the movements of contaminants below ground. So I'll say let's meet at 5 or 10, and we'll continue learning about including adsorption and retardation factors. So I'm going to pause recording. Okay, so far we learned if you have a contaminated site, and if you know the porosity, if you know the hydraulic gradients, you could be able to predict how fast contaminants can move, assuming they don't stick with the soil. But in the last class, you learned that contaminant can stick with soil if they have high organic carbons. And some, even they don't have organic carbon, they can also stick based on different types of reactions that we didn't really cover. Um, but either way, if they stick around, then that means the pollutants will not migrate. And the parameters that you are interested to predict that is KD. KD is adsorption. It's basically if it's a linear adsorption, which you can assume for most pollutants in groundwater because their concentration range is very small. Is basically concentration of contaminants in a soil divided by contaminant concentration in water. So if that's the case, then you'll be able to predict what's the contaminant concentrations in water. Um, what we do is we will be able to calculate FOC times KOC, and again FOC, KOC is some constant times, I'm just going to say alpha or a constant or a constant times KOW. And KOW, you'll be able to, you can get this info from any thermodynamic constant, like if you search KOW of a constant of a pollutants, organic pollutants, you'll be able to get that number somewhere in a table. If you can't find it in a reference, I'll be able to help you. So from literature, search on Google Scholar. So any information you don't find this kind of parameters, search the pollutant name and KOW, you will be able to find that information in some site, and then you will be able to use them.
Excuse me, Professor?
Yes?
I think you had a question in the group chat during break.
Okay, let me check. Just to clarify, higher porosity means greater number of pores, which are smaller, allow for storage, greater storage capacity, whereas something that is more porous, greater size of pores and smaller in number, allow for faster movement of pollutants. Trying to distinguish between porosity and porous. Okay, I think this is an important point. porosity means how much pore space inside it. It doesn't say anything about the individual pore size. Okay. So when you say porosity, I'm just going to write here. Porosity means total pore space. Okay. So that means sum together all the small pores all together. And it doesn't really say anything about individual pore size. It doesn't say anything about individuals pore. Okay. So that individual pore size depends on the actual particle size. Okay. If individual particles is bigger, that means when they come closer, there will be bigger gap in between. Okay. So I think pore size increases if particle size increases. So think of this way: if you put a small bead or a smaller ball inside a container or a bucket, you'll have lots of pore space. You have a very small amount of pore space. The reason is they'll be packed close together. But if you put like a bigger ball inside a bucket, you will have a lot more pores in between the particles. So that is pore size. Pore size means this. So this is pore size, okay? If the particle become bigger, so that means it's the pore size increases. So the porosity, see that's the porosity is really not a good indication. So unless you know the particle size, you can't really determine the velocity. Okay. My internet has been really suspended. I think I may have missed a question. Okay, it's all recorded, so you should be able to hear it later if you miss something. All right, so now what we're going to do is we're going to recalculate the same thing if we have different amounts of adsorption. But I give you some example here, groundwater, more examples, because you will have that same thing in your project. So I'm just going to write it here and see if you can relate to these questions. Estimate the rate of groundwater entering the existing plume. Leachate from a landfill leaked into the underlying aquifer and created a dissolved plume. So you have a landfill. So let's say this is your landfill. Okay. And this is your, so this is your soil, and this is landfill, and this is your groundwater table. Create a dissolved plume. Use the data below to estimate the amount of fresh groundwater that enters into the impacted zone per day. The maximum cross-section area of the plume perpendicular to the groundwater flow is 1,600 square feet. So that's maximum cross-section area, the plume perpendicular to the groundwater flow. So basically, you are saying that if this is groundwater, it's basically saying what's the amount. Think of this cross-section area. So this one is, that area is 16 square feet, because that's the perpendicular to the groundwater flow. Groundwater gradients means that head differences and all that, dH over dL is 0.005. That's why it doesn't have a unit. Hydraulic conductivity of the soil is the is a 2 point. So K is 25,000 gallon per day per square feet square. So that's a different unit. You used to see a unit um, which is basically a time distance over time, but here it says gallon per day, which is volume per day divided by square feet area. So we have to account for that unit conversion. So this is just a question. It's a similar question. The only difference is the units are different. So what it says that you have a pollutants that comes here. Let's say this is the pollutants, and then it goes like this. So it says how much it will be diluted by this groundwater flow. Basically, how much the flow of a groundwater in that area coming in. So again, it says that it will estimate the fresh amount of groundwater that enters that zones. So basically, how much water flow through this cross-section area is what you are calculating. All right, so if we calculate that, the flow is, K dH over dl. That's the hydraulic conductivity times gradients times area. So K dH over dl area, everything is given. The only difference is that the unit you have to check. So let's write that one. dH K is 2500 gallon per day times divided by square feet. That's the unit here. And dH over dl is 0.005 times area is 1600 square feet. So if you see, everything else is cancelled. The only difference is square feet will cancel. There is no unit, so the answer will be gallon per day. And that's exactly what it says, amount of freshwater flow. So if you multiply this, what's the number? 2500 times 0.005 times 1600. Yes, that's. So why? So that's again, this is a very straightforward question, but let's see where you might use this. So if you are doing something, let's say polluted site, and you want to know how much water is going to dilute it, this is the way you can calculate. So this is applicable for those kind of problems in your project. Let's say another example. There was a spill of an inert substance into subsurface. It's similar as previous one. The spill infiltrated into the unsaturated zone and quickly reached the underlying water table aquifer. So it's the same question. So let me start with us. Let's say this is the spill. Okay. And this is surface. So this is surface. And spill occur here. And then this is the groundwater. And it says it quickly move in unsaturated zone. So this is unsaturated zone, saturated. So then this will move, let's say this moves here. Okay. And this is groundwater. Move these directions. The aquifer consists of mainly sand and gravel with a hydraulic conductivity of 25. So K is 2500 GPD per square feet. So that's the same thing as before. Effective porosity is 0.35. Static water levels at the well neighboring to the spill is 560 feet. So if you have a groundwater well, so if you dig a hole, imaginary hole, dig well here, and this height is let's say H1 at that location is 560 feet. And that in another well, 1 mile down gradients means towards the way that water moves. So if you move 1 mile distance, if you have a well here, the height decreases and that become S2 become 550. And the distance is 1 mile. So it's asked you determine the Darcy's velocity, okay, seepage velocity, and the velocity of plume migration, and how long it will take for the plume to reach a down gradient well. So it asks you time, velocity of plume migration means contaminant velocity, seepage velocity, that's the velocity of water, and then this is velocity of Darcy's velocity. Okay, you know that velocity of Darcy's velocity is k dh over dl. Velocity of water is Darcy's velocity by porosity. So if you know the other one, then you can calculate. And here it doesn't say anything about contaminants, so that means, or it doesn't say the contaminant whether adsorbed or not. That means the contaminants move as fast as water moves. So that means you can write this same as VW. And then time is basically distance divided by velocity of contaminants. Okay. So if you calculate one, you should be able to calculate everything. So I'll tell you where most of the students, at least some students, make mistakes when they calculate dH over dl. So let's start with BD is K times dH over dl. That means H1 minus H2, L1, L2. So you have to think of which direction the distance increases. So distance here L1 is 0. Here L1, this direction we are changing along the groundwater directions is 1 mile, or L2 is 1 mile. So H1 here, whatever the height at that location, wherever you say L1, you have to define that. H1 is 560 and H2 is 550. So a lot of times people, what they do is they switch. When they switch, the answer become negative, and that's not actually, you have to always see which direction water moves. So as long as you are consistent, the sign will cancel out. So you will not get a negative number. So if I write this one, K is 2500 gallon per day feet square feet times H1 minus H2. So H1 is 560 minus 550 divided by L1 minus L. So let's see. Okay. There is a negative term now, so I see why it is happening. Actually, there is a negative sign somewhere, otherwise this answer will not make sense. Velocity of dH over dl. There is a negative sign here, otherwise this doesn't make sense. So that negative sign, I miss all the places, because what it means that dH over dl, the head is going to drop as the L is increases. So that means this sign will have a negative number. That's why.
Professor, is there a mistake on slide 18?
What's that?
For your Darcy velocity on slide 18,
Yeah.
I guess it shouldn't be there.
Darcy's velocity is, this is Darcy's velocity.
Yeah, there shouldn't be an A, because then that would be for your Q. It should just be like KDH over DL, right?
Oh, you're right. You're right. So that's the one. That's the typo there. Yes, right. Okay, so I'll tell you where because I know that last class they made mistake. Then I realized this is a thing I want to confirm here. So a lot of times when I write this one, Darcy's velocity is k dh over dl. This number is always given as, last time I said 0.005. So it's a positive number. So anytime you get a negative number, that because we switch it. So it has to be positive, otherwise it's not going to change. But just know that dh over dl, the way it works is the height is always going to drop when the length increases, because as it moves, it's going to drop the way. So that's why the every time it shows a negative number, we have to account for that one over there. So another way to write is this will be dh over dl. That means this is always positive if you write that number. So now I did the same way and I got a wrong number. Wrong number means there will be negative term, and which doesn't make sense. So let's say L1 equals 0 minus L2 will be 1 mile. So now the answer will be correct. The only thing that will be a problem here is because your velocity is negative. What does that even mean? It means that it moves opposite direction of which way we write the coordinate. So I think velocity cannot be negative unless you are looking for directions. That's the only way it looks. So you get this number here. That will be 2,500 gallon per day times square feet times, this will be 10 feet divided by 1 mile. What is the 1 mile in square feet or the feet? 1 mile to feet.
5,280.
5,280 feet. So let's say if I write this one, I'll write first, then I'll explain. So 2,500 times 10 divided by 5,280. So that's a 4.7 gallon per day. Let's see. Square feet. So now the velocity looks like weird here because it's a gallon per square feet. If you do change to distance over velocity or distance over time, then you have to change gallon per square to cubic feet. So if I write 1 gallon to cubic feet or 1 cubic feet to gallon is 7.4, so that will be 4.7 gallon. You know that 1 cubic feet is equal to 7.48 gallon. Then you have day feet square. So that way you can change gallon and then you get the number as feet per day. So that answer will be some feet per day. That will make more sense in terms of velocity. So once you do this one, everything else is the same thing, because then you divide by porosity, then the rest of them are already we solved it. So I'm not going to solve other, but one thing I want to emphasize here, because that's where a lot of times we make mistake, or you can see how I got this number. So anytime you have dh over dl, always write the same distance wherever the h1 is associated with the distance where you start, and h2 will be the further distance. As long as you switch the same direction, you should get the answer. And velocity always account for that sign over there. Any questions on this particular problem? And then there is a one example here. I am not going to solve it because we already solved all of them. So we should try to solve on this particular problem using this one. So I will say do it yourself. The last one we are going to learn is the when you account for the adsorption. So I want to say how it works. So think of this way. If you have a pollutants, imagine this box. If you start injecting a pollutant, if you say this is a time and this concentration, let's say time 0, you start injecting, and as the time process, that concentration increases. So let's say this is like a box input, means this is how the profile of a concentrations. What that means is t equal to 0, this is t equal to t. So that means at time t, until that time you are injecting certain volume, then you stop it. Okay, so what's the concentration will look like? In the effluent, it takes some time before it shows up. So let's say this is a very small one. So immediately, if it is entire pipe, there is no no soil inside it, then you will see the effluent will be like this. Okay, effluent concentration will look like that. Exactly same thing, because you are just moving the concentration that way. But if it is a soil, then it will start dispersing, right? So that's why it is going to start looking like more like this. It will disperse and then it will go like that, a little bit far away. And then it will start dropping like this. So this is with porous media. This is empty pipe. So if you just injecting a pollutant in a pipe, this will exactly then how you inject the concentration profile will exactly look like that. But if you have some porous media, then it will disperse like this, and this is because of dispersion. And the way it works is, if you write it properly, then it will look like this. It takes some time to appear on the outside, so that means whatever because it takes some time for this pollutant to move from here to here, you will not see anything until then, right? So what happens is, in that time, some pollutants may short circuit and appear faster. Some pollutants may take some time to appear later. So that's why, if this is how to expect, normally what you see is 50% shows up. This is 50%. Shows up when you expect everything to show up. Partly and some of them move faster because of that short circuit and all that. And some slow down because some pollutants will move like this. Because of this dispersion, you will see this dispersion coefficient. And this is how far it spread, that's is the dispersion. This is dispersion. And if your pollutants start absorbing, the entire things will show up much later. So that means if this is dispersion, but no adsorption. But if its adsorption is there, then it is going to show up like this, let's say. So this is dispersion plus adsorption. What it means that it takes a lot longer before the pollutant starts showing up, because it has to saturate all the soil. So that's how you'll see the concentration profile, influence versus effluent. That's exactly is showing it here. Adsorption or retardations. That all it means that contaminant plume will slow down, or it takes a lot longer before it appears at the groundwater well. So I just wrote the equation, which you are not going to use it, just to explain what does that mean. So if you have a groundwater well and you are looking for the concentration change over time because of pollutant coming in, it depends on groundwater velocity or advection. So this term is advection. What it means that, as I said, advection depends on velocity. So change in concentration in that well will be because of the the flow of water. So how much pollutants can just move into that well because of velocity. And then this one is dispersion. So this is the dispersion coefficient. So this is a constant. So as you see, so that's why it's called advection dispersion equation. And this doesn't account for anything that absorb in the soil. But if you are accounting for how much it changes in a system, it also depends on how much it in water as well as how much in the soil. So this is concentration in water, change in concentration in water. This is change in concentration in soil. Okay, so that depends on exactly how much change in water, how much in dispersion. Because what it means that if you are accounting for how much pollutant change in a small area in a groundwater aquifer, you have to account for both soil as well as changes in water, because it will start absorbing. So if you put everything in that equation, we basically get the same equation as here. The only difference is you have a constant term here. If you divide that one, all it means that this equation is for pollutant transport, and this equation for water transport. Okay, and if you see, the difference is that the pollutant transport is retarded. This is almost like velocity of pollutants, velocity of contaminant. So that means if you see this term is velocity of water, that means this entire term must be related to velocity of pollutants. Just if you compare equivalents. So that's why now we call it velocity of contaminants is velocity of water divided by retardations that are because of adsorption. And so that's why you see over here, retardation is velocity of water. Well, if you rearrange this one, R equal to velocity of water divided by velocity of contaminants. And always velocity of contaminants will be either less than or equal to velocity of water. It will never exceed the velocity of the water. That means R value is always going to be greater than equal to 1. If it is 1, if R equal to 1, that means it's no adsorption, or it's conservative. If R is greater than equal to 1, that means it's sticking to the soil. And this R, as you see in this equation, that's related to this value. It's ball density times partition coefficient KD divided by porosity, and KD is FOC times KOC. All right, so what it means that if you know what is the KOC value, if you know how much FOC value, you'll be able to predict how far the contaminants will move, how long it will take. Exactly what we did before, but just the only difference is you can now velocity of contaminants will be different from velocity of water. In this case, that means in this example, like we equate velocity of contaminant equal to velocity of water, you will not be able to do that if you have retardations. That's the only difference. So I'm going to show you example. Again, I just saw that these all depends on the porosity, ball density. So retardation factor is increases. That means it slow down. The ball density increases, the porosity decreases, and the adsorption coefficient increases. And adsorption coefficient is KD, and KD increases if the organic carbon fraction increases, and KOC increases. So this is FOC, this is KOC. All right, so that's all in terms of the equations. Let's solve this example. That's the end of this class then. So the aquifer underneath a site is impacted by several organic compounds, including benzene, 1,4-DCA, and pyrene. So basically, I gave you all these value. KOW for all these values given. Okay, so that means you know the you know the KOC value. So KOC here is 0.63. So that means the KOW is, if this is given, log KOW is 2.13, implies that KOW is 10 to the power 2.13. So that's how we got 135. So anyway, so that means if you know KOW value, you know the KOC. Estimate the retardation factor using the following data. So I ask you just simply calculating the retardation factor for all these values. So let's calculate for just one value, benzene. Retardation factor is 1 plus ball density times KOC times FOC divided by porosity. So 1 plus ball density is given 1.6 gram per centimeter cube times FOC is 0.015, KOC is 0.63 times KOW. KOW is this one for benzene is 135. So 135 divided by porosity. Porosity is 0.4. So by the way, this KOW, the unit is opposite to ball density most of the time. So I didn't write the unit anywhere. So you might confuse how the unit is got cancelled here, because retardation factor doesn't have any units. So this is a KOC unit is centimeter cube per gram. Okay. So that will be 1 plus, so 1.6 times 0.015 times 0.63 times 135 divided by 0.4. So that's 5.1. So that's 5.1. So this will be 6.1. What it means that compared to the water, benzene will move 6.6 times slower. That's all it means. All right, so at least based on this class, you should be able to calculate how fast it's moving. The only thing I'm going to say is that how do you know the soil properties if you have a site? So I'm just going to give you in 30 seconds how to find that out. But on Friday, I will show you exactly. So if you have a site, you can use this method to find the soil properties. So I'm going to share the Google's soil, my Google Chrome. What I did is I searched soil survey USGS. Then you go to this site and then you say start here. It will open up a software. And now what it says that you will see the entire US map. So if you know the location, you can go to that location and it tell you the soil properties. Means if porosity or that value you might be able to find. Or mostly it will give you hydraulic conductivity. That way you know whether it's a, so let's see, if you want to do it, let's say you go to soil map. No. Oh, you have to search or address. So let's see Los Angeles or UCLA. I don't think UCLA. Let's say 420 Westwood and Los Angeles. Let's say your site is there. So it says where you want to go, and it says 420. It gives you some selected site. It's both are same. So I'm just going there. So you see the Los Angeles, and you want to know, this is the UCLA map. And let's say you want to know where is the soil site in this location. So you can create this if you, let's zoom in. Let's zoom so that we can see. I could not see why it is not zooming in. I know we probably lost the entire thing. So let me see view. Okay. So let's say you want to draw the area over here. So I'm just going to draw here. And I want to say that, okay, I want to know what soil type it is here. So once you, I think it's a little bit sensitive. You have to go all the way there to complete it. Okay, so now it says this is a site. This is my site where I want to know the soil type. And then you go to the soil. It says that one. Then you go to soil map. It says what kind of soil. So you see, it says 100% this soil. And if you click that one, it gives you all this information related to soil. So it says 75%, all that stuff. And then this is where you'll show the slope is 0 to 25% because that's a hill over there. So that's why it says. And 2 to 12%. Then you just let's look for. All right. So this is where the KSAT or the saturated hydraulic conductivity says 0.6 to 2 inch per hour. So this is the K value. And it gives other number, but this is what you want to find that out. And if you say what other things are there, it just says that. So this is how you can find, if you know which sites you have, if you know the locations, you should be able to find the K value for your site. So, and soil properties. And anything you don't find, that's why I say anytime you look for a soil site, you should be looking for the information related to the site. All right, so that's all in terms of today's class. You should, hopefully you'll be able to calculate the speed at which contaminants move in your homework question. So I'll release the homework tonight. It's due 1 week from now. And good luck for the quiz. I don't set any questions which is not on the slide. Okay, so if you read the slide, you should be able to answer the quiz. You don't have to read the handouts. Okay, I'm going to stop recording.